In section 5.3, we're going to be learning the double angle and half angle identities. So in these identities, if theta is some angle, then when we take the cosine, sine, or tangent of twice that angle, so double the original angle, we have some identities to find that new value of cosine, sine, or tangent. Cosine has three possible identities that you can replace cosine of 2 theta with cosine squared theta minus sine squared theta, or 1 minus 2 sine squared theta, or 2 cosine squared theta minus 1. These are all interchangeable. We can replace one with another. Okay, so if I'm finding the cosine of 2 theta, I can pick whichever one's easiest. Or if I see one of those that's highlighted in red, if I see that in the verification of an identity, I can replace any of those with cosine of 2 theta. Sine of 2 theta only has one identity, so that is just 2 sine theta cosine theta. Okay, that's times in there. And then the tangent of 2 theta also only has one, and that is 2 tangent theta over 1 minus tangent squared theta. So let's look at using these, okay? If we are given that the cosecant of my original angle is -4/3, all right, we know that theta is in quadrant 3. So my x and my y are both negative. So I need to figure out, first thing, is find values for x, y, and r. So cosecant is 1 over sine. Sine is y over r. So cosecant of theta is r over y. My radius is going to always be a positive number, so that's the +4, and then the negative goes with the y for -3. I need to find x, and you may be thinking this is a 3, 4, 5 special right triangle, but in that one the hypotenuse is 5. Here the hypotenuse, otherwise known as r, is 4. So we have to use our Pythagorean theorem. So x is going to equal the square root of r squared minus y squared. But because I'm in quadrant 3, it's going to be the negative value of that square root. So that equals negative square root r squared is 16. -3 squared is +9, so I'm going to subtract a +9, which is the negative square root of 7. It may be helpful next to, since we know we're going to be using sines and cosines and tangents of theta in our identities to find the cosine, sine, and tangent of 2 theta. So we're just going to find cosine of our original theta equals x over r, which is -√7 over 4. Sine of theta equals y over r, so that is -3/4, and our tangent of theta equals y over x, so that one is -3 over -√7, which simplifies to just be 3 over √7. We'll actually leave it there for now because we're going to be plugging that into things, so we won't rationalize now. We'll rationalize at the end of using our identities. Our next step is simply to use the identities. The first one we want to find is the sine of 2 theta. In this case, we only have one identity, so that is 2 sine theta cosine theta. 2 is just a number, so it stays like that. Now we're going to use our sine of theta, which we figured was -3 over 4. And then our cosine theta was -√7 over 4. A negative times a negative is a positive. And if I remember that 2 is just 2 over 1, I can multiply all my numerators. 2 times 3 times √7 is 6 root 7. Again, the negative goes away because it's negative times a negative. And then the denominator is 1 times 4 times 4, which is 16, which I can further simplify because both the numerator and the denominator are divisible by 2. So when I do that, it becomes 3 root 7 over 8, which is my sine of 2 theta. The next value that I want to find is the cosine of 2 theta. I can pick any of the 3 identities because they're all equal. We'll pick the first one. So that is cosine squared theta minus sine squared theta. We're just going to plug in our values. Cosine is negative root 7 over 4, and that's squared. Minus sine is negative 3 over 4, and that is squared. So the root 7 over 4 squared, the negative goes away, and so it becomes root 7 times root 7 is 7. 4 squared is 16, and it's positive because it's a negative times negative. And then again, that's going to happen in the second parentheses, but 3 times 3 is 9, 4 squared is 16, and I do have common denominator, so I can combine those. So that is 7 minus 9 is negative 2 over 16, which simplifies to negative 1 over 8. Our final value we want to find is the tangent of 2 theta. Again, here there's only one identity to use, so that is 2 times the tangent of theta divided by 1 minus tangent squared theta. So when I plug my values in here, that is 2, and then the tangent of theta is 3 over root 7 in the numerator. The denominator is 1 minus that same 3 over root 7, but now squared. That's ugly. So let's look at this. The top simplifies to be 6 over root 7. The denominator is 1 minus 9 over 7, because 3 squared is 9. Square root of 7 times itself is 7. Okay, now that becomes 6 over root 7 divided by 1 is 7 sevenths. So 7 minus 9 is negative 2, and then sevenths. So this is divided by negative 2 sevenths. Since dividing by a fraction is the same as multiplying by its inverse, we can change this to be 6 over root 7 times negative 7 over 2. We can go ahead and simplify a little bit first, so that becomes a 3 and that becomes a 1, otherwise known as 3 times 7 is negative 21. We'll pull the negative out in front, and then the bottom just becomes root 7. All I have to do now is rationalize, so I multiply the top and the bottom by the square root of 7. I'm left with negative 21 over root 7 over 7, but 21 divided by 7 is 3 over 1, so this becomes simply negative 3 root 7. In our next example, we're going to verify a statement, and in this case, tangent squared x is definitely my simpler side, so this is my goal. And I recognize that the cosine of 2x, I can use my double angle identity, so we're going to replace that, all right, with something that we know. I can again pick any of the 3 cosine identities. So we're actually going to work this 3 times, once with each of them. So let's start with the first one. So we're going to say 1 minus cosine squared, we're going to use x instead of theta since our variable is x, minus sine squared x, all times secant squared x. We're going to distribute secant squared into my parentheses. So I get 1 minus cosine squared x secant squared x. minus sine squared x secant squared x. But that's all there. And now I need to distribute in my negative sign. So the negative 1 goes in. And then 1 minus cosine squared x secant squared x plus sine squared x secant squared x. Now, what I want to do is use that very first strategy where we want to turn things into sines and cosines. So in this case, 1 is still 1. Cosine is cosine. But secant is 1 over cosine. So this is over cosine squared x. My second term is sine squared x. Oops. And then secant squared x is, again, 1 over cosine squared x. This first fraction becomes 1. So that is 1 minus 1. And then I'm left with sine squared of x over cosine squared of x. 1 minus 1 is 0, and sine over cosine is tangent. They're both squared, so it becomes tangent squared x. So I've met my goal. Now, let's do this again, but with the second cosine identity. Again, we start with 1, but now we're going to replace our cosine of 2x with 1 minus 2 sine squared x, and then secant squared x stays there. Again, I'm going to distribute secant, and I'm going to distribute the negative at the same time in this one. So this becomes 1 minus secant squared x. And then a negative times negative is a positive, and it'll be 2 sine squared x secant squared x. So I want to simplify this last term, so I'm going to take secant squared of x, and I'm going to replace that with 1 over cosine squared x. So this becomes 1 minus secant squared x plus 2 sine squared x over cosine squared x. So this is now tangent squared x, and we'll replace that in the next line. And the other thing I'm going to do is secant squared x has an identity involving tangent squared. And so I'm going to replace secant squared x with tangent squared x plus 1. And then my last term becomes 2 times the tangent squared x. And now 1 minus 1 goes away. And then I have a negative tangent squared x plus 2 tangent squared x, which just equals a positive 1 tangent squared x. And again, we are done. We have verified this identity. Once more with the third one. Hopefully we're starting to see the pattern here. So 1 minus our third cosine double angle identity is 2 cosine squared x minus 1 times secant squared x. Going to distribute in the negative secant squared x. I have 1 minus 2 cosine squared x secant squared x, and then plus a positive secant squared x. 1 minus secant squared x is 1 over cosine squared x, so this is 2 cosine squared x over cosine squared x, so that's going to go to 1. And then my final term is plus secant squared x, so this is 1 minus 2 is negative 1 plus secant squared x, which if I rearrange it becomes secant squared x minus 1, which you will recognize from our Pythagorean identities as tangent squared x, and we have verified our for the third time. We also have half angle formulas. So if theta is our angle, then we can find the values of sine, cosine, and tangent of half that angle, or theta divided by 2. And so if we have this, we have one equation for sine, one equation for cosine, although note that there will be 2 possible answers for both of those. And then tangent of theta has one that has a plus or minus, and then there are 2 other identities. In example 3a, it says to use half-angle identities, so we know we're going to be using one of them. We are looking at the sine of pi over 12, and we could use the sum or difference identities for sine, but we've been told what to do, so we're going to follow directions. And so sine of pi over 12 means that pi over 12 is theta divided by 2. That's our half angle, which means that theta equals 2 pi over 12, or pi over 6. All right, so in order to do that, my first step needs to be to find theta. After that, I have to figure out what goes into my identity. Because my sine half-angle identity involves cosine, I need to figure out the cosine of pi over 6. The cosine of pi over 6, otherwise known as 30 degrees, is square root of 3 over 2. Now, I get to plug this in, and I get to use my identity. So the sine of pi over 12 is going to equal the square root of 1 minus the cosine of theta is root 3 over 2. And then the denominator in that is 2. There are several ways to simplify this. Personally, I like to take this, and because I can see that there's going to be some things that cancel, I'm going to split my fraction to be 1/2 minus root 3 over 2 divided by 2. All right, and so that tells me that this is just 1/2, but then this is root 3 over 2 multiplied by the inverse of 2, so 1/2, which means that 1/2 minus root 3 over 4 is 2 over 4 minus root 3 over 4. And when I simplify that, we're actually going to be a little bit bad, and we're going to leave a radical within a radical. And so the square root of 4 in the bottom becomes 2, but the top becomes the square root of 2 minus the square root of 3. In example 3b, we're going to take the tangent of 165 degrees. Now this is not one of our angles we memorized on our unit circle. You could think about dividing this by 2, but that gives us a fraction as our degrees. And we definitely didn't memorize any of those. So maybe 165 equals theta divided by 2 instead of us dividing 165 by 2. Which means that theta could equal 330 degrees. Now that one we did memorize. So again, we want to start with finding what's in our identity. So tangent, all of them have cosine of theta, and then some of them use sine. We can pick any of them we want to. For our purposes right now, we're going to pick the one in the middle because the denominator looks the easiest, so we're going to do that. We need cosine and sine, so the cosine of 330 degrees is root 3 over 2, but the sine of 330 degrees is negative 1/2. So let's plug those into our identity. So 1 minus our cosine of theta is root 3 over 2, and that is the numerator. The denominator is sine of theta, so negative 1/2. So this becomes 1 minus root 3 over 2 times negative 2. Thank goodness for multiplying by the inverse of a fraction. All of a sudden, this becomes a little bit simpler. I'm going to distribute that negative 2. So I get negative 2 plus 2 root 3 over 2. Those go away. And I am left with negative 2 plus root 3.